Hello everyone and welcome back to our series about teaching maths in the FET phase. Let's first start by taking a look at our video on the topic of geometric sequences. Geometric sequences have lots of applications for the banking and business world. Interest and returns on investments, appreciation and inflation, depreciation and deflation are all examples that involve a multiplying factor or percentage. They can therefore be analyzed using principles of geometric sequences and series. At Bambazi High School in KwaZulu-Natal, Mr. Tanozi Dlamini is introducing his learners to geometric sequences. The outcomes for the learners are to find a common ratio for a sequence of numbers and use it to categorize the sequence as a geometric sequence, and to write down the formula for the general term of a geometric sequence. The teacher begins the lesson with a revision of arithmetic sequences. Learners are required to determine the common difference and the eighth term of a given arithmetic progression.
If the learners did not have the background on arithmetic progression, they won't be able to deal with geometric progression. So learners must know, they must move from the basics to something that is complicated.
The learners determine the common difference by subtracting each term from the next term.
So the difference between the first and the second term must be equal to the difference between the third term and the second term. So which means T2 minus T1 should be equal to T3 minus T2.
Next, learners use the general formula for an arithmetic sequence to determine the eighth term.
Term 8 is equal to
A plus, open the brackets,
2,
n minus 1
n minus 1
into d.
In this formula, A represents the first term, n is the number of terms, and d is the common difference. After substituting the numbers, the answer is 23.
Please make sure that you read the activity.
In this activity, the teacher presents learners with a real-life situation where a farmer has 2 hens and a cock. Each hen can produce up to 6 breeding hens for the next generation. The farmer wishes to develop her farm over 5 years. If she only breeds each generation once, how many young breeding hens will she have after 5 generations? Using real-life situations in mathematics helps learners to see the relevance of what they are doing.
Mathematics is not something that ends in the class, so it must also be put into practice in the outside world. So that is why we are trying to take something that is practical from the outside world and put it here and bring it in the class.
For the first question, learners must show that they understand what is required from them.
What have you been asked to find out? You've got 3. How many cocks will be born? Is it the correct answer? How many cocks and hens will be born in 5 years? Is it the correct answer? How many young breeding hens she will have after 5 generations?
We are choosing 3. Is the youngest breeding hens will she have after 5 generations? You see that?
One of the biggest shortcomings in maths is that learners don't understand the question.
A language is a problem really here in mathematics generally. So the student can't be able to express themselves. If they can't express themselves, they can't even understand the concepts, mathematical concepts.
The worksheet supplied has a table with columns indicating each of the 5 generations. Learners must fill in the rows, which indicate firstly the number of hens born on the farm in each generation, as well as the proportional increase in the number of hens. The teacher walks around the class and notices that learners are treating the problem as an arithmetic sequence. He explains on the board.
How many hens will there be in each nesting box after 1 generation?
6.
The teacher draws the 2 hens and each of their 6 chicks.
So this is a first generation. So how many hens do we have here after the first generation?
12.
Let us look at this hen also. So this hen also has got the ability to produce how many hens here?
6.
Also, this one also has got the ability to produce how many here?
6.
6 also here. And
After
also here,
explaining the principle, the learners continue on their own with the third generation. They draw the chicks themselves.
draw it and do this.
72.
So after the third generation, you'll have how many?
72.
And then you proceed to the fourth generation, the fifth generation.
Now learners have developed a pattern and are able to complete the table.
How did you find this 2,592?
492 times a 6.
Times A6.
Yes, like
Why
this.
did you multiply by A6?
Each hands it produces 6 from each generation.
We have come to 2,592 as a total number of chicks in the fifth generation. Right now, if you look at your table now, you are expected to calculate now the ratio or the proportional increase in the number of chicks moving from the first generation to the fifth generation.
At first, learners do not use the formula but are aware of the proportional increase.
We got the 12 in the second generation from multiplying the 6 hens with the first generation, and the number from the second generation we multiplied it with the 6 hens so that we got third generation. And they took the third generation, multiplied it with 6 hens, and we got 432. And we took the number from the fourth generation and multiplied it with the 6 hens to get 2,592.
The teacher explains the formula for the common ratio.
Our common ratio will be determined by taking a term and divided by another term will give you a ratio. Right, let us look at the movement again here. We have moved from the first to the second. Now to determine a ratio, which means we'll divide the second by the first to get the ratio. So which means the ratio of ours here will be this T2 divided by a T1. And also the ratio between this term and this term, because this is a second and a third. So it will be a term 3 divided by a term 2. So you'll see the pattern. You'll see the pattern. Let us use this formula to calculate.
Learners use the formula common ratio. R is equal to Tn divided by Tn minus 1, where Tn is the nth term. In this way, the common ratio is determined to be 6. Mr. Dlamini will now define the geometric sequence.
The geometric sequence can be defined as the list of numbers which can be obtained by multiplying the previous number by the common ratio to move to the next number.
It is clear from the table that our sequence of numbers is a geometric sequence. Now that learners have determined the common ratio, the teacher will work with them through the worksheet to develop the general term for a geometric sequence.
What would you say is the first term of the sequence?
The first term of the sequence is 2.
So he has taken it as our first term as a 2. And then let us move to the third question. How many young hens will be on the farm after 5 generations?
2,592.
How many times did you have to multiply the common ratio to get to the 5th term?
It's equal to 4. Because around these spaces of the ratios.
I took the ratio and multiplied it with the fourth term to get the 5th term.
So we've got to multiply the ratio 4 times to come to the 4th term. Describe the 5th term, T5, as a product in terms of A and in terms of R, with the exponent that expresses the number of times the common ratio was multiplied.
The 5th term is equals to A times R to the 4th exponent.
The teacher writes this formula on the board and then tests this formula with the first term and the common ratio.
So how many times did you have to multiply the common ratio to go to the 5th term? Is 4 times. Right, what is 6 into the fourth exponent?
1,296.
Let us multiply now 1,296 by 2.
2592.
So the answer that we obtained there is the total number of hens that were obtained on the 5th generation.
The fifth term is thus expressed as the first term multiplied by the common ratio to the power of 4.
If you wanted to move from this 5 to this 4, if you want to move from 5 to 4, what are you going to do to this 5?
5 minus 1.
Right now, let us write this equation in full. So this equation was A times R into the 5th minus 1, isn't it? So this is...
Using this information, the teacher gets learners to express the general term Tn in terms of the first term A and the common ratio R raised to the power of the number of terms to be multiplied.
Tn is equal to A times
This
R
will be
exponent n.
A times R into what here? Into a known number of terms minus 1. So because our aim is to determine the unknown number of terms, so which means this will be n equals to A times R into n minus 1.
The learners have established the general term for a geometric sequence to be Tn equals the first term A multiplied by a common ratio R to the power of n minus 1. In the final activity, Mr. Dlamini gets learners to say whether this is an arithmetic or geometric sequence.
12.
It's a geometric sequence.
Why do you say it's a geometric?
We use a 2 to multiply to get the following term.
Learners are reminded of the differences between the arithmetic and geometric sequences, especially related to the common difference and the common ratio.
Our kids tend to confuse the two issues. So if we don't stress on the concept of the common ratio and the common difference, and where the common ratio belongs and where the common difference belongs, so they tend to confuse issues.
He will now get learners to apply the formula to determine the value of the 10th term of this geometric sequence.
Right, let us calculate T10. Right.
This learner has substituted 3 for her first term and multiplied it by the common ratio 2 to the power of 9.
1536. So which means the 10th term will be
1,536.
1536.
Another learner writes the actual values on the board and tests the results.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It means that the answer is correct.
Using this geometric progression, this can help us. So a kid now can be able to go back home and tell a mother, if a mother is selling maybe chicks or what, that you must expect so much number of chicks in so much years. So making use of this, the knowledge that they've acquired here on geometric progression.
Now that you've seen our video, time for us to welcome our guests. We've got Smangaliso Twala, who's an independent maths consultant. We've got Paul Appelsamy from Diversity and Transformation Solutions. And we've got Taska Matlejwane, who's a principal at Pafokgang Secondary School. Thank you for joining us. The first question to you, Taska, why was it important to relate the geometric sequence activity to hens?
Firstly, it was good to awaken learners that maths that we do comes from real life. By quoting an example from real life, it conscientizes them that whatever is going to happen in class, it's about the practical life out there.
Okay.
Excellent. Yeah, I think just to add to that, the area is a poultry farming area, and you know, very real to kids in that particular place. So I think something that would really draw them to attention in terms of, hey, this is maths, it's in the real world.
Brings it closer to home.
It's very close to home.
Okay, Smangaliso.
Bring reality to class.
Okay. Paul, what are the main difficulties learners have with geometric sequences, and how should teachers help them?
Okay, I think the fact that geometric sequences introduces ratios which are common, I think straight away provides a problem, because we know the kind of difficulties kids have with fractionals and with exponentials. Now, one of the concerns I pick up from the video is that the teacher did not use the opportunity to introduce these as his introductory comments, but rather went to arithmetic sequences, which I'm not so sure is a basis for geometric sequences. I would have reviewed concepts like fractions, how do we multiply them, how do we divide them, because that's used in the lesson. I would have reviewed concepts like exponents, you know, clarified basis indices, and even done some exponential work. Often we find that the arithmetic in this particular aspect is very, very lacking. Okay, so I think that kind of approach as an introduction to the lesson in terms of reviewing prior concepts that are used here would have helped a little bit more when it came to the hard calculations within the geometric sequences.
Tasker?
Yeah, I agree with what Paul said, and over and above that, I would say a lot of difficulties are coming into a lesson because of misconceptions. We as educators introduce a lot of misconceptions in terms of bringing examples or inappropriate examples or examples at an inappropriate time. Like, for instance, what Paul has quoted now, bringing in arithmetic series is good, but you may end up confusing learners. Rather be confined to the subject that which is at hand, and also to go further, to define these terms, to know exactly what a ratio is. Terms that which were initially quoted like depreciation, appreciation, those are terms that which need to be defined. And they would come so nicely into the lesson because they are things that which are used in everyday life. So I feel a lot of problems are around the language. If language can be clearly defined and be cautious when you use words in a lesson, you'll avoid a lot of complexities.
Okay, Smangaliso?
Yes, I picked up something else from this video that the teacher is actually doing that can actually cause difficulties with the lesson of geometric sequences. He, when he was describing the nth term, the formula for finding the nth term, he's actually using wrong words. He's saying it's the nth term, it's equals to a times r into n minus 1, which is completely wrong.
What should he be saying?
He should have said the nth term, it's equals to a multiplied by n, multiplied by r to the power n minus 1, instead of into n minus 1.
So that does cause confusions for learners.
It does.
Okay.
So
but then, Paul, would you like to add
I'm just
again?
saying the progression again. You know, how do we go so fast into that particular question of what is the end term? There are no other examples put on the table. With one example, we get there. Sure, do the practical example, which really brings it down to home, and then put a few more on the table. Let them construct their own geometric sequences, and then we can try and get to what a generalization is and get to rules and formulas. And it will be much better and much more concretized because these kids have seen it work.
Smangaliso, do you think the teacher managed the class well?
If we're just to look into the arrangement of the classroom itself, you would say yes, it's a bit better in that the children are in groups and in a way they're working in pairs. That's what I saw, and they are actually talking to one another. But if you go deeper than that in terms of the lesson itself, I wouldn't say that he has done a good job there.
Any suggestions?
Suggestions would be he could have allowed the children to be in groups and work as groups, and then from there they need to report to the whole group, to the whole class as individuals. What is it that they have actually discovered? And it shouldn't be just one example. You cannot make a generalization out of one example or just two. You need about 3 examples, different examples that are related in one way or the other.
Okay.
Just to differ with Spagna a bit, I think the classroom is very effective in the sense that these kids are engaged. To find kids working with an example that comes out of the blue, it presents difficulties in terms of what is a ratio, how do I find this common ratio? And here is a classroom that seems to be actively engaged in trying this. Okay, with a couple of prompts from the teacher, you know what, guys, look at this first generation, look at the second generation. I think he's done good there. I think he really has done good there. I think maybe what could have been, a little bit more is the questions and the way he introduces them, the opportunity, what he offers to them could have been a little bit more structured in terms of giving direction without throwing an answer. Okay, there's T1, and then there's Tn. So, but I think he's done well in terms of managing the class.
Okay.
Yeah, I would say yes, done. In structuring the class, yes, done very well. But however, he would have gone further in terms of structuring questions, probing questions, direct questions to lead learners to precisely the formula that which he wants them to discover. Lead the learners towards discovery rather than giving it to them. I think that that would be the better way.
That takes us to our next question. Smanga, do you think, or at least what do you think of the teacher's use of questioning in the lesson?
The questioning wasn't so great, but it needed a bit of improvement. Here and there, he was actually asking the children a question and then follow it up with a thought-provoking question. So like, how do you know why? It mentioned something like that, but it wasn't enough. That's what I would.
The basis was there, though, you feel?
Yeah, the basis was there, but it wasn't enough. There were not enough questions that were actually provoking the children, except maybe the whole problem of the chickens. That one is actually very good.
Oh?
Yeah, the structure in terms of that particular example should have been a little more leading in terms of, you know, guys, we're looking to find this out. Because you'd notice that prior to him speaking about the generations, the kids were pretty lost. But how do they come up with numbers and fit them into this particular pattern? So I think therein, you should have structured it a little bit more, and not just leave the questions at the end of the example, you know, at the end of the exercise. I think those could have been handled a little bit more effectively in that sense. You know, follow-on questions.
Chaska?
Yes, I would say you should have made it further clearer in terms of the way the fouls are going to be reared, because that fine example can come up to be a most confusing example. Because like, for instance, those of the first generation and the second generation, you don't know whether those of the first generation are maybe being sold out or why are they not considered and so on. You should have made it very clear that we consider generation by generation, not that the first one is no more producing. Okay. Because if the first one produces, it's going to produce some kind of a Fibonacci type of numbers now, which is no more the sequence that which the person wanted to achieve.
Okay. Any other issues, Taska?
Yes. Like they've said about language, my advice to my colleagues is that language is very important in the teaching of mathematics. We need to be very careful and cautious when we say it, because the confusion that which we leave with learners can live long thereafter and create a lot of more misconceptions. And then also, like for instance, when you talk about the ratio, we always take it that is Tn plus 1 divided by Tn. But why is it like that? Why is it not the other way around? Like for instance, you divide the second term by the first term, the third term by the second term. But if you do it the other way around, it's still a ratio. But why not use that one? Those things should be clarified to learners.
Okay. Smile.
Yeah. Again, the definition of geometric sequence, I think that he should have left that towards the end for the children to come up with that. And after having done a lot of experiences, having gone through a lot of experiences, then they will be able to say, by the way, this behaves different from what we know, which is an arithmetic sequence.
Okay. Well, that's all we have time for. Thank you very much for joining us. And thank you to our viewers at home and at schools for joining us. Do keep your eyes open for Module 21 coming soon. Thank you and goodbye.